Hypothesis testing. Okay, so I believe that the easiest way to show you how hypothesis testing is going to work is I'll walk through an example and then we'll go through and I'll show you the math and the formula and formalize the technique that's behind it. So, Jill the mind reader. So Jill says that she can read your mind and you decide to put this to the test. So you grab 5 cards and you're going to draw a card. She'll guess what that card is. You'll put it back in the deck, shuffle up, pick out another, have her guess, and you're going to repeat this process 10 times. So the key here is that we're going to make an assumption. Right? We're trying to prove whether or not Jill can read our minds. So we're going to assume, right, that mind readers aren't a thing. Let's assume Jill is not a mind reader. Well, if she's not a mind reader, she's just guessing at the card that I'm looking at. And in fact, she could guess correctly. Since there are 5 cards and she's guessing, she has a 1 in 5 or a 20% chance to guess correctly. So when we conduct the experiment, we're going to get an actual result and find out how many she does guess correctly. Now, let's say, for the purpose of this example, she gets 5 out of the 10 correct when we play this game. So the proportion of correct guesses she actually did get was 50%. And so this already sets up what's the debate. Should have gotten 20% correct, got 50% correct. So if she was not a mind reader, 20%. Now, you might be tempted to say, well, she just proved it, right? She read our minds. She got 50% correct. But that's really not taking into account something that probably already sprung to mind for most of you, and that's that there's a chance, right? There's a chance she could have guessed all of them right. So what we need to account for is that Jill could have, by chance, gotten 3, 4, 5, 9, 10 correct, right? Even though she was only supposed to, quote unquote, get 20% correct. In other words, what if Jill's just lucky, right? She just went to guess wildly and she got lucky. Well, in particular, we want to know then, how lucky did she get? Right? Because we don't just want to hand wave and say, oh, she got lucky. It's important that we be able to describe exactly how lucky she would have gotten. So how likely is it that Jill could have guessed 3, 4, 9 of them correct? Because it is possible, it's possible that she's just guessing and she guesses more than 2 out of 10 correct. And importantly, it's really likely, right, that she gets 3 correct. It's highly unlikely that by chance she got 9 correct. So we're going to need to know the actual probabilities of these things happening. So let's recap where we are right now. 3 key things that have happened. The first is we assumed that Jill could not read our mind. We witnessed her actually get 5 out of 10 correct, and we need to keep in mind this whole time that she might have just gotten lucky. In terms of Jill reading our mind, this is the proportion of time Jill was going to guess correctly out of all the times, right? We just played the game 10 times, but ideally we could have kept doing this 100, 1,000, 1,000,000 times. This assumption that she can't read our mind is actually a statement about the population of all guesses she would ever take. So this is a statement about the parameter. So we use P to represent that. We say P is equal to 0.2 or 20%. Next, we saw that Jill actually did guess 5 out of 10 correct. So this is from sample data. This is what we witnessed her do. So this is a statistic. P hat equals 0.5. So now that we got something symbolized here, if she's just guessing, this would say the parameter is 0.2. What we did witness was a p hat of 0.5. So now we're ready to answer the question, how likely is this to have happened? since our assumption is that Jill's guessing, her guessing will actually follow a normal distribution. More on this in a second. So we can calculate a standard score for this. Again, I'm showing this here. Go back and watch this after we finish the video. I don't want to focus too much right now on where these numbers are coming from. But Jill's performance was 2.3 standard deviations above my assumed parameter. The next thing we need to handle is that she got a z-score of 2.37. That is, she got 50% correct. But if she had done any better than that, it would just be even stronger evidence that she was reading our minds, right? If she'd gotten 60, 70, 80% correct. So this means that we actually want, in terms of our normal curve, to shade everything to the right of 2.37. From our z-table lookup, we see that the shaded area to the left of 2.37 is 0.9911, which means that the shaded area to the right, spoken correctly here, the unshaded area there, the region to the right of 2.37 is 0.0089. Which means that we're ready to make a decision here. The decision before us, is Jill not a mind reader, or is she a mind reader? So if she is not a mind reader, we just witnessed something that only happens 0.0089 or less than 1% of the time by chance. So how lucky did she get? She just did something that only happens 0.89% of the time. So roughly 9 in 1,000. The other decision we can make is that she is a mind reader. For this to happen, we would be forced to admit that she did something so astronomically rare that she can't just be guessing. So how lucky does she need to be before we have to admit it wasn't luck, right? How do we determine where this decision line lies? Well, in practice, we need to decide where that line is before, right? Before we did the experiment, Jill and I should have made a decision, right? How good does she have to do to prove herself, essentially? In this case, however, her probability of what she accomplished is 0.0089. That is so exceedingly small that we would have to conclude that yes, Jill is reading our mind, right? Or cheating, right? But the point is, this is so rare that you have to admit that Jill is doing something besides just guessing. So now let's try to formalize this idea. And the first concept we're going to need are hypotheses. So a hypothesis is a claim or statement about a parameter. Note that when we made the assumption about Jill, we didn't assume what she would do in the experiment. We assumed what would happen if she kept guessing always, right? For all of time, all of the guesses she would ever make, 20% of them would be correct. In hypothesis testing, then, we usually want to determine if some treatment has had an effect on a population. So when a change in some characteristic of a population is associated with a change in another characteristic, we call it an effect, right? For instance, if we want to show that playing music in the background while students take a test or read, we would conduct an experiment and ask if the playing of music in the background had an effect on their reading scores. So a hypothesis is a claim about a population. So it is going to be used as an assumption about a parameter. In hypothesis testing, one which is to show that an effect has occurred. So typically we form these two conflicting hypotheses. The null hypothesis is H sub 0, right, called H null sometimes. The alternative hypothesis I'm going to represent with an H sub A. The null hypothesis is typically a statement of no effect. right? The shoes didn't make me run faster. The medicine didn't make me better. The music in the background didn't improve my reading score. Often, this is the opposite of what you want to show is true, assuming we're making an effort to prove that something is effective. So this is what already starts to seem a little backwards when you take a step back, right? If I want to show that my shoe makes you run faster, I don't directly show that it makes me run faster. I disprove the idea that it doesn't. So I assume the shoe doesn't make me run any faster, and I try to disprove that statement, which means that the alternative hypothesis is often the one we want to show is true. So for Jill, the null hypothesis was the assumption she was guessing. In other words, that the parameter p, the proportion of correct guesses, was 0.2. Jill is just guessing. The alternative hypothesis was p is greater than 0.2, right? She's better than just guessing because she's somehow reading our minds. Importantly, the alternative hypothesis doesn't make a statement of just how good she is at reading our minds, right? She didn't say she was perfect at it. It just says she's better than chance at it. Now, it gets a little difficult to figure out which one is which, so I want to give you some guidelines. The original claim can be reflected in the null or the alternative, depending on how the claim is worded. Yes, typically the alternative is the one that we want to show is true. But no matter what the original claim is, we're always going to need to form this null and alternative hypothesis. You will always assume that the null is true when performing a test of hypothesis. So to figure out which one's which, we need to identify the specific claim being tested and then convert that, right? Write it out symbolically so that we can use it in our formulas. So we give the symbolic form that is just the opposite of the original claim above to figure out what our alternative hypothesis is going to be. Of the two above, the alternative will be the one that does not contain a greater than equal, or a greater than or equal to, less than or equal to, or equal sign, right? The alternative hypothesis will have no equality in it. The null hypothesis will always contain a statement of equality. The last thing I want to note here is that, again, hypotheses are statements about parameters. So they will be statements about the population proportion or the population mean. So let's run through an example here. Let's say that I have a claim that the mean IQ of stat students is at least 110. Well, one of these claims is clearly that the average test score, the mean test score for the population for every stat student, that's a parameter, is greater than or equal to 110, right? At least 110. The opposite of that statement would be that the average is less than 110. So one of these has an equality in it, right? The mu greater than or equal to 110, that one is going to become my null hypothesis. The other one's going to become my alternative. My alternative stays just as it is. My null hypothesis becomes that the mean is equal to 110. So I drop the greater than part. We have to do this because we're going to need a solid assumption about what the parameter actually is to conduct the test. So let's try one more. The percentage of men who watch golf on TV is not 70%. The claim then is that the proportion, P, again a parameter, is not equal to 0.7. The opposite of that claim would be that it is 0.7. The null hypothesis becomes the one with the equality. The alternative becomes the one without. So the alternative hypothesis for the scenario is that P, the proportion of men who watch golf on TV, is not 70%. leaving the null hypothesis to be the statement that the proportion of men who watch golf on TV is 70%. So let's go over some definitions real quick. The test statistic is the number you compute from the sample data. So it's going to be used to decide if we're going to reject or accept the null hypothesis, right? In the Jill mind reader example, we were determining if the assumption Jill's not a mind reader was true or false. It's going to be in terms of a standard score, a z-score. So it's going to tell us how many standard deviations our sample mean was above or below our assumption of the parameter. So all of this is captured in the p-value. The p-value is the probability assuming the null hypothesis is true. I can't stress that enough. We're going to assume the null hypothesis is the true statement. So then we're going to calculate the p-value, which is the probability of what we just observed, right? Assume the null hypothesis, do the experiment, and then calculate the probability of what we just witnessed. So this means that the smaller the p-value, the stronger the evidence against the assumption. And that could be a little counterintuitive, right? But keep the Jill mind reader example in mind. I think it's just really nice to have one concrete example that you carry around with you that you can, so that you can see how this works, right? We assume the null is true. So if we witness something that's really rare, it suggests that the assumption of the null hypothesis was not true. This relies on the fact that what we witnessed, the statistic for the Jill mind reader example, that is that she guessed 50% correct, the 5 out of 10 correct, that's not up for debate, right? That's not an assumption. We witnessed her do it in the experiment. So if something's got to give, it's going to have to be the assumption that she was just guessing. So that p-value of 0.0089 is really strong evidence, because if she was just guessing, she just did something sort of miraculous. If she had done even better than that 50%, the p-value would be even smaller because it would be even harder to do by chance. So let's look at this visually, because this is where I think it all comes together. We're making an assumption, right, for the Jill example, that p is 0.2. That is, if she's just guessing, that guessing is in fact a random event. So sometimes she's going to guess more correct, sometimes she'll guess less. It's easier for her to guess a couple more right than it is for her to guess a bunch more right than she should. So we have a normal curve that is centered at 0.2. So our assumption gives us this normal curve and tells us where it's centered. This curve is representing the sampling distribution under the assumption that the null hypothesis is true. So this sort of curve will come into existence, right? Our sampling distribution will happen no matter what type of experiment we're doing. This often is in reference to taking a sample, right? So if we're doing a survey, the random behavior there is picking the people that you send the survey out to. So next, we need to layer on top of this what we actually witnessed. In this case, we witnessed her the p hat of 50%. We saw her actually guess 50% correct. This has a standard score, a z-score of 2.37. So 2.3 standard deviations above average. So everything to the left of that 2.37 represents cases where Joe would have guessed less than 50% correct. This is the number we can look up on our z-table. And when we look it up, we see that it's 0.9911. Well, we wanted the probability that Jill would do 50% or better, because that would be stronger evidence that she is reading our minds. So we shade to the right, that is, we take the 0.911, subtract it from 1, we get the 0.0089. So this p-value of 0.0089 was, sum it all up here, we assumed the curve was centered at 0.2, but Jill's performance, right, assuming she was just guessing, would only occur with probability 0.0089, that p-value. Since that's really, really rare, it's a strong indicator that our assumption that the curve should be centered at 0.2 is incorrect. The last sort of part to mention when we finalize this is the significance level. So the significance level for a test is the probability at which we agree or reject the null hypothesis, right? It's that decision line, right? How exceedingly rare does the observation, the statistic, need to be before we reject the null? It's usually represented with an alpha. And two common values you'll see used are 5% and 1%. So in our example, in purple here, you'll see our p-value represented on our picture. You can see it is the 0.0089. I've shaded about 0.9% of this, the area under this curve, purple. But before we did the experiment with Jill, we should have made this agreement on the significance level, right? What does she need to do to prove to us that she's reading our minds? Well, here you can see that her performance, again, is below those two standard values. If I shade the area under the curve in yellow, we'll see that, and it's kind of layered on top there, but we'll see that there is more yellow than purple, right? So if we set that alpha level of 1%, we are saying that we will reject our null hypothesis if the p-value is less than that. Now, we could still be making a mistake here. Jill could have gotten really lucky and we'd be making a wrong conclusion, but this is only going to happen 1% of the time. So for a significance level of 0.01, we're only accepting a 1% chance of incorrectly rejecting the null hypothesis. That is, could Jill have pulled a fast one on us? Yes. What's the chance of that? 1%. Now, this is with all the typical caveats, right? This is assuming we've done a proper experiment, that we've followed all of the other research methods properly. There is a big difference in our alternative hypothesis, though, to saying that the average is less than 180 versus saying the average is not equal to 180. If our alternative hypothesis looks something like the mean is less than 180, in this case, we'll be shading to the left, right? Everything that's less than a certain value. And it's represented on my curve here in blue. I've shaded everything less than some hypothetical value. However, if I'm stating it's not equal to, any observation that happens that's really far away from 180, really far above will count, and really far below will count. So in this case, we call it a two-tailed test. An area in both tails will count towards that p-value. Let's try one last example. We're going to look at a mean this time instead of a proportion. So the New York Times article noted that the lifespan for 35 male conductors was 73.4 years. The lifespan for all males is 69.5 years. Again, for the population, for everyone. So let's assume that we have a standard deviation of 8.7, and we're going to use a significance level of 5% to test the claim that male symphony conductors have a lifespan that is different from the population average of 69.5. So we're going to start by identifying the variables. Our sample size was 35. Our average, the mean for our sample, right? The statistic is 73.4. We're told that the standard deviation for the population is 8.7, and we're using a significance level of 5%. We need to form our hypotheses. Remember, there's statements about the parameter, so it won't be statements about X bar, about the statistic. They're going to be statements about the population. The null hypothesis will be the statement that our male conductors are no different. That is, that our male symphony conductors have a mean lifespan of 69.5 years. Our alternative, since we're trying to show that it's different, is just that that mean is not equal to 69.5. We find our test statistic, that is a z-score of 2.65. Importantly here, the parts in green, right, we are assuming. How did I know what the population parameter really was? How do I know that mu really is 69.5? I'm assuming it. The whole test relies on the fact that we are assuming the null hypothesis to be true. So I'm going to look at our table. I'm going to use it to find out what the shaded area to the right of z equals 2.65 is, right? Our test statistic. In this case, I get 0.004. However, this is a two-tailed test. Our test statistic was significantly high, right? It was a large value over 69.5, but my claim was that it's just different. So the fact that it was so far above is just as compelling as if I got an answer that was really far below. So I'm also going to shade the same area on the left side of the curve, representing what would have happened if I'd gotten an extremely low answer. You combine those to get a total shaded area of 0.008 for our p-value. Now that we have our p-value, we're ready to make our conclusion. The p-value of 0.008 is less than our significance level we were testing, 5%. So we're going to reject the null hypothesis. Conclusion, male conductors have a lifespan that is different from the general population. We are not concluding they live longer. We're not concluding that they do not live as long, right? We can just say that it's different. So these formulas have been skipping over. Let's go over them now. The test statistics, how am I getting those? If you want to test means, you're going to calculate a z-score. You're going to take the x bar, the statistic we just witnessed, subtract the assumed mean, divide by the sample standard deviation s, divided by the square root of the sample size. If you want to do a test on a proportion, the test statistic is that standard score z equal to p hat, the statistic that we witnessed, minus the assumed population proportion parameter, p, over the square root, again, of that assumption, the assumed p times 1 minus p over n.